Exercise 13A. We're going to revise. We're going to revise your index laws. We've learnt this back in year 7, and you practiced in year 8, year 9, more so in year 9 and year 10. And some of you may have gotten it well, some of you haven't. Some of you will remember the first few laws, but struggle with the second half of it. And my goal is to make sure to get you proficient with each and one of those. Okay, so if you think about the chapters we've done so far, there are a few things that you need to be able to take down. One, you have to be able to use your algebra. When I say algebra and solve, you've had quadratics, factorize, null factor law, solve, right? You had your cubics, factor theorem, cubic division or synthetic division, and then null factor and solve, okay? Same thing when you got to gallery graphs, you did rectangular hyperbolas, you did square root functions. All of that was inverse operations to solve. So now when you go to exponential and logarithms, it's the same idea. In order for you to sketch a graph and analyze, you have to be able to solve algebraically. And the only algebra that we've got so far, which comes back to inverse operations with index laws. Okay? And then same thing with logarithms. You're going to learn logarithmic algebra before you sketch. Okay? It's always like that. You're going to have to learn an algebra to it to solve, and then you're going to sketch it so you can analyze it. So same thing towards the end of the year, you're going to do circular functions. You'll be doing the same thing. Okay, so here we go. Let's start off with some easy algebra. Let's have a look at this one. 2 to the power of 3 times 2 to the power of 12. What is the simplified, if I want to simplify the following? So 2 to the power of 3 times 2 to the power of 12. What does that simplify down to? Can I please have, let's go with Trent.
2 to the power of 15.
15, that is correct. Now, Trent said 2 to the power of 15. How did Trent get his answer? Can you describe that to me, Will? What did he do to get 2 to the power of 15? What did he do?
He just added the, what's it called? Powers together.
Good. You add the powers together, so it's 2 to the power of 3 plus the 12 gives you 2 to the power of 15. But my question is, because a lot of students will know this, right? You can ask them and they'll be able to tell you just add the powers. The problem with just adding the powers is when I give you other problems, sometimes they don't know what to do and they're like, just add the powers, maybe times it. I don't want you to do it with a question mark. I want you to be able to tell me why this is the case. Because if you know why, then every one of these problems should be easy. It's when you don't know why and you're trying to memorize the rules and you forget. So my question is, why do you add the powers? What's the reasoning? Because I told you so? Because you learned in year 7? What's the reasoning for it? Because Mr. Dickinson said so. Alright, 2 to the power of 3 plus with that 12. Why is it 3 add the 12? I don't understand why we add them. What's the reasoning? Someone explain to me. There's only one simple concept to it. Why do we add the powers? Let's instead of doing 12, what if I gave you 2 to the power of 3 times 2 to the power of 2? We know that it's going to be 2 to the power of 3 plus 2, 2 to the power of 5. I want to know why we add. There. Very good. When we do, if you really think the progression, what you've done, primary school you learn addition. That's the very first thing you learn. The operation that you first learned was addition. Then after you know how to add single digits, potentially double digits, after you know how to add, you learned after grade 1 and 2, you learned multiplication was repeated addition. So if I gave you 2 plus 2 plus 2 plus 2 plus 2, you would tell me this is 1, 2, 3, 4, 5 groups of 2. And so what we learned in grade 3 was that a shorthand of writing this or simplifying it would be 5 groups of 2. Will. We've got 5 groups of 2. So when you've learned multiplication, that was just a short way of doing repeated addition. By the time in grade 3 and 4 you learned multiplication, then division, then do your fractions, you got to year 7. Year 7, we said, all right, now you know your times tables, hypothetically. Not all year 7s know the times tables. But let's say they know their times tables. Then they say, well, what if I changed it to 2 times 2 times 2 times 2 times 2? Year 7 was the first time you learnt how to write this shorthand. there had to be another method. Instead of saying 2 plus 2 plus 2 plus 2, we said 5 plus 2. Then there had to be a short way of saying 2 times 2 times 2 times 2 times 2. And what you learnt was we wrote it as a power. We said, all right, well, in year 7, this is what you learnt. You wrote 2 to the power of 5, which actually meant 2 times 2 times 2 times 2 times 2. Now the cool thing here is because once you make that sort of new rule, and it's not really a rule, it's just more of how you write things. Once you say it's 2 to the power of 5 represents a repeated multiplication, then now you look at this one now. See, if you break this apart, it makes a lot of sense. 2 to the power of 3, you would tell me that means 2 times 2 times 2. 3 of them. That's what you would say. You would say repeatedly multiply 2 3 times. See? 2 to the power of 3, this is what it means. And then you said times again. See, that's the key factor here. See, if I put addition, you can't do it. That's why we always do it times. If I put addition, you can't add them. But you can times them. See, if I put a times here now, I put a times, and then I say 2 squared, actually just means 2 times 2. So if I wrote it down now, 2 times 2, see, it's repeated multiplication. They're all repeated multiplication. I haven't done anything. 2 to the power of 3 just meant that. 2 to the power of 2 just meant that. I'm timesing them all together. So suddenly, if I just remove this and I said, well, is there shorthand of writing this? There was. It started off by saying, what's another way of writing this? And they just said, just put a little 5 on top. And let's say that represents this. And it just so happens that, well, if you're counting them, you had 3 of them repeatedly multiplying. And now you have another 2. Logically, you would say 3 plus 2 makes 5. Does that make sense? Because if that makes sense, and the reason why I'm emphasizing this, we can jump to the next rule. I'll jump to the next rule, which is a further one down the track where most students make the mistake here. When I give you this one in year 9 or year 10, 2 to the power of 3 squared. Anyone remember the rule for this one? What do? You do 3 times 2. So you'd say 2 to the power of 3 times 2, and you write 2 to the power of 6. That's law number 3. Now my question is, why is that? Why do you times it? Because if you understand the first theory, this all makes sense. Everything comes from the first one. If you understood the first one, which was literally started off by a representation, why do I times 3 to the 2? Can someone explain it to me? Yeah. Remember, if I didn't put a 2 cube here, if I gave you 3 squared, what would you have said to me? You would have said, 3 squared means 3 times 3. So if you write 2 cubed squared, it just means, this is what it means. This is actually what it means. It means 2 cubed times 2 cubed. Agreed? When you say 3 squared, you say 3 times 3. So if I said 2 cubed squared, you would say 2 cubed times 2 cubed. Yeah? But then, funny enough, 2 cubed, we know that is actually 2 times 2 times 2. And then this is also 2 times 2 times 2. And what you end up with is, well, if you've got 3 lots of 2's here already, and you times it with another 3 lots of 2, then I've got 2 lots of these 3's. I've got 2 lots of these. I've got 2 lots of these 3 groups. So 2 lots of these, or 2 groups of 3, make 6. That's essentially what you're doing. You're saying 2 lots of the 3's. That's what. So if I put a 5 here, you're just saying 5 lots of these. 5 lots of the 3's makes 15. That's the logic, okay? So now that you've got sort of an idea, the reason why I'm emphasizing these two is the common mistake most students make is with the cubes when you're timesing them, or when you're timesing them, they add. Another mistake, or common mistake that most students make, is if I did 2 cubed plus 2 to the 4. Because you're so used to doing the times and you get a problem like this, you're like, oh, maybe the rule is 2 plus 2 gives you 4, and 3 plus 4 gives you the 7, so you write 4 to the power 7. Alternatively, you might still think this is the times and you write 2 to the power 7. Okay, and I don't want you to do that. Don't do it blindly. Look at the problem. What do you have? Does it make sense? And then you write your answer. Okay? So, I've just covered 2 rules with you there, and we're just now going to jump to D. So if you understand what I was saying, let's do D now. 3a squared b cubed times 4a a cubed b cubed. What does that become? What does this simplify down to? Let's go with Hamish.
times 2, plus the 2 and 3 and the 3.
Good. The 2 and the 3 with the 3 with the 3. So, what he is going with is he's saying a squared can be multiplied to a cubed. Okay, because we're actually just saying 3 times a squared times b cubed times 4 times a squared times b cubed. If I write it out for you to see, all I'm really saying here is I'm saying 3 times a squared times b cubed times 4 times a cubed times b cubed. We already know how to simplify a squared times a cubed, which is why Hamish said you add the powers, 2 with a 3. So it becomes a, 2 plus 3 is 5. But then you follow the next one, you can say, well, b cubed times with b cubed is the same thing as 3 with a 3. So 3 plus 3 gives you b6. What else am I missing here? So I've done the a's, I've done the b's, and I'm missing 3 times 4, which we know how to simplify that. 3 times 4, 3 groups of 4 is the same thing as writing 12. So I can say 12. But 12 is being multiplied to a fifth, a to the power 5, and it's times to b6. So we just write our answer as 12a5 b6. Is that easy? Rule number 1 and rule number 3. That's all I've gone with. Okay? Next one. Let's do A. X to the power 4, y to the power 3, x squared, y squared. How do I simplify this now? What are the rules again, Finn? What do? How do I simplify this problem? Takeaway. Can someone now explain to me? Yes, you're right. You can write it as x to the power 4, take away 2, and y to the power 3, take away 2, which gives you x to the power of 2, and y to the power of 1, which is y. This is your simplified answer. But, you see, I'm not interested in the rules because you learned that in year 7, 8, 9, 10. You can memorize that all you want. I'm more interested in why is that true? Because once you know why it's true, you can play around with the algebra as much as you want. You can do whatever you want. You can play around with however you want to start it off. It's up to you. Especially when we get to the 2 last rules, that's the one that most students forget. And I want you to be able to play around with that. I can't manipulate the equation. Why do we take away? Yeah, you could take it talking about the x's.
So if you expand both.
Expanded both, yes, I've got x times x times x times x.
Then if you just cancel out the like term.
All right, that's a very good point. So when you said cancel out the like terms, what are you saying?
Product of x is double x there. And there's double x on top. That's the
Yep, what do they become? When we cancel things out, what do they become? Do they just disappear or? Simplified to what? To 1, very good. I want you guys to see this problem here. This is going to lead into the negative rule, but I want you to see what Finn said was correct. X to the power 4 divided by x squared. What you learned in year 7 was to say take away the powers, 4 take away 2, x squared. What I'm interested in is, well, why is that true? Well, you have 4 on the top. When you divide, you can split up fractions here. This is the same thing as saying times 1 times 1. Now this is a fraction here. That's an x on an x multiplied to x on x again, multiplied to x over 1, multiplied to x over 1. See, I haven't changed anything. I've just expanded. I've just expanded. X to the power 4 is 4x's on the top. X to the power 2 is 2x's on the bottom. Now, as a fraction, I can separate numerator and denominator because they're all timesing. So I've done x over x times x over x again. But over here, there's no other term, so I can put in a 1 over 1. Doesn't change anything. X times 1 times 1 is the same thing. If I have 1 on these, then you can see x divided by x is equal to, what is x divided by x? No. What's 2 divided by 2? What's 3 divided by 3? What's 5 divided by 5? 1. So when you go x divided by x, it's exactly the same thing. You're just saying how many x's fit in x. All of these cancel out to be 1. So what are you left with? 2 of these x's. Yeah, left with 1. What you can see is you have 4 on the top and you divide them, you're losing. That's why we're subtracting. We're saying I had 4 on the top, I'm dividing 2 on the bottom. So obviously I'm going to lose 2. So 4 take away 2 gives me 2. That's why we take away. Okay? That's why rule number 2, it works that we take away the rules. Now, a more interesting question. If x to the power 4, you can cancel it out, then what if I gave you now x to the power of 3 divided by x to the power of 5? Using the same logic, this is the same thing as saying x cubed divided by x fifth. Okay? This is the same thing. You would say to me, using the rule, you would say x to the power of 3, take away 5, x to the power of negative 2. What's x to the power of negative 2 look like? That's now going back to this, I think that's the 6th rule. What's another way of writing x to the power of negative 2? Going back to year 9 and 10, what's the rule? What can you rewrite? How can you rewrite x to the power of negative 2? 1 over x squared. Now, see, this is your other rule. Why is it 1 over x squared? I don't want you to memorize that, because if you memorize that, you're going to make this mistake or you forget to use them. Why does it work? Shh. Following what Finn said before, if you expand it and do exactly the same things you just did, x cubed on the top just means x times x times x. I've got 3 of the x's on the top. X to the power of 5 on the bottom just means x times x times x times x times x. So I've got 5 of them on the bottom. Now if I do exactly the same thing I just proved to you, that if we separated the fractions, x divided by x, x divided by x, and x divided by x is going to cancel out to be 1, 1, 1. So it makes sense if you had 3 on the top and you have 5 on the bottom, well, if you're going to cancel them out, you're going to lose 3 on the bottom, you're left with 2 left. That's why we can write our answer as 1 over, and now you've got x times x, and we can simplify that as 1 over x squared. And using rule number 2 that you learnt, you can take away the powers. You can link these two and say, oh, well, x to the power of negative 2 must look like 1 on x squared. And that's your 6th rule. Okay? And you can use the same rule to prove that a to the power of 0 is equal to 1. How do you know that? Same thing, if I gave you a to the power of 3 divided by a to the power of 3, naturally you would say that's the same thing as saying a cubed divided by a cubed. And that also means a times a times a divided by a times a times a. And again, you got 3 a's on the top, 3 a's on the bottom. If you divide them, they all cancel out to be 1. See, it makes sense. Every rule that you've learnt so far, there's 7 rules in total for index laws. They come from this. Okay? Now, I've got two last rules for you to remember. What does this become if I do this? What does this become again? Very good. It is a to the power of 6, b to the power of 9. How? A to the power of 2 times 3, b to the power of 3 times 3. And this logic comes back from rule number 1. You're just saying you got 3 of these doing a squared b cubed times a squared b cubed times a squared b cubed. You got 3 lots of 2's and 3 lots of 3's. That's why it becomes a to the power of 6, b to the power of 9. Okay, so that's the second last one. Now, I've covered most of the rules here so far. Does anyone realize I'm missing one? What's the one last one in year 10 that a lot of students find this a struggle?
The one with square roots and
Very good. What was the rule again? There is a square root in this one.
a to the I can't remember what it is, but it's like a to the y over x or something with like the square root and then x is the root number. But I can't remember what y is.
Very good. So if I gave you a to the power of m over n, what is this equivalent to again? This is the last rule that most students forget. And the reason why you forget is because it doesn't make sense to you. That's why. Okay? So, a to the power of m on n. Yeah. Thank you. A to the power of m on n. What was the rule again? There had a square root in it. Yes, there was a root. There's an a. Where does the m and n go? Logically.
N goes like the nth root or something.
Very good. N is the nth root, so n is on the outside. So if you had a 3 on the bottom in the denominator, then it becomes a third root. If you had 4, it's fourth root. If you had a 2, it's square root. Where does the m go then?
Outside.
Outside of what? Well, you could. Yes, you could do it that way. Traditionally, the rule would have it where? Where's the m go? You got the n, where does the m go? All right. I'll write it down. Write that rule down. In case you forgot. Let's make sure to copy that down. That's your last rule that most students forget. That's a year 10 rule that would have been introduced at the time because you learned surds. Okay? A to the power of m on n is equivalent to nth root of a to the power of m. What's an example? I'll give you an example.
Wait, so what number?
A to the power of 5 on 3 is the same thing as writing third root of a to the power of 5. Okay? Now, if you're wondering where this rule comes from, listening, where the rule comes from actually goes back to what squares are. Now, remember when you write a squared, let's say a squared equals 4, okay? What is a equal to in this case? Square of what gives you 4? Square of what gives you 4? 2. So you know a equals 2 in this case, right? Now, because a squared equals 4, if you're squaring to get to 4, how do you undo a square again? What do you do? Square root. So to go backwards, you got to square root 4. Agreed? So root of 4, if you root 4 on the right-hand side, then the question is, what does root of a squared, because what would that become? Now, you know root of 4 is 2, and you know the answer has to be a. So the question is, how did root of a squared become a? That's the question. Okay, so that's the question that you want to ask yourself. You want to say, what has happened with the square root symbol to make it a? When you say a, that's actually to the power of 1. Okay, so the question is, how did square root of a squared equal to a1? Something has to happen with the square root and the 2. Now the only way for a 2 to become 1 is if you divide it by 2. Which is why another way of writing this is a squared, if you're multiplying this to the power of half. I'm just going back to the same rule as what you did before. This is the same thing as saying a squared times half, which is why it becomes a1. And that is why we've told you, since you learnt in year 10, we said a to the power of half is equivalent to a square root. That's why we call it a square root. Okay, we've got squares, square roots. So that means using this logic, if half 1 over 2 being the denominator, then if you want third root, for example, a cubed, the only way to cube root it is it had to be a cubed times 1/3. That's where it's coming from. Okay? All right, here we go. Just before you all practice the skills, we're going to do 2 last examples. I want you to copy this down because these are the 2 common ones that most students find difficult. C, copy this one down. C, 3/4 to the power of -3. How do I simplify this? What I don't want you to do, which is what most students do, when you put a -3, this is what most students will write. They'll write 1 over 3/4 cube. Because it's negative power. So you know that the rule a to the power of -m is equal to 1 over am. That's the first rule that most students go to. So if I gave you a to the power of -4, you would say it's 1 over a4. So because I gave you a -3, the likely tendency is to write it as 1 over 3/4 cube. Now you can do that and it will work. Why do you think this normally stumps students? What's the issue? Why do you think students don't like this? Or they stop here? What's the problem? Yeah, fraction on fraction. Students aren't generally good with fraction. So my tip, you can do it this way. I'm giving you a different way. You can do it this way, but I want you to think about all the rules you have. When you have a power, remember you can times the power. That's what we learned before. We said a to the power of 2 to the power of 3. You said you can times the powers. So why don't you just times the powers? You don't have to make it a fraction. You can still keep 3/4 and say this is the same thing as saying 3 to the power of 1 times -3 over 4 to the power of 1 times -3. Isn't that much easier? It's much easier to work with at that point. Okay? Now, when you write this, this is now 3 to the power of -3 divided by 4 to the power of -3. Okay? At this point, we don't leave our answers ever with negative powers.
Yes.
Now, the way that your teachers may have taught you in year 10 is if you have a negative power, you can switch from top to bottom and bottom to top. Yeah? So what your teachers may have said, I'm not sure if that's what they said, but if they did, they might say this now becomes 4 cubed, and this one will switch down and become 3 cubed. Okay? I'm not a big fan of that, but if that helps you to do these kind of problems, then you can. Can anyone explain to me why that is true? Why does that work? Why can I say if it's 4 -3, I can just switch it to the top and say it's 4 cubed?
Because when you're timesing two fractions, or dividing two fractions, you do the switch.
Absolutely. If you break this apart and you actually think everything goes back to if you break it apart. If you break out the mathematics, it will all make sense. Everything that you learned so far comes from the basics. So, if I can just rub this off, which is not happening. Okay, here we go. If I actually wrote out what you could see, 3 to the -3 is the same thing as writing 1 over 3 cubed. Divided by 4 -3 is the same thing as writing 1 over 4 cubed. But remember with fractions, when you divide fractions, you can write it as 1 over 3 cubed times 4 cubed on 1. That's why it becomes 4 cubed, 3 cubed. Okay? So either way, what I'm trying to show you is don't memorize, you can use the techniques I'm showing you to make it easier for yourself. I like to keep them as simple as possible. I don't like doing fraction on fraction unless you're really good at fractions, which in general most students aren't. So if you're good with it, stick with this. But if you're not, you can simplify your problems. It's up to you how you want to do it. Okay? Alright, here we go. Last problem for the day. And then you can go on to exercise 13A. I'll give you the questions sheet as well. And that's it for today. Last problem. I want you to do B. Simplify B. Use all the skills you've learned so far. There's 7 rules in total. Make it as easy as possible for you. Don't make it harder. Simplify where you can. And I want you to see whether my method is quicker or your method is quicker or which one's easier. You find your own way, because there's a lot of ways to approach this. You can do the division first. You can get rid of the negatives first. You can expand it first. It's up to you. But I want you to get the correct answer. Okay? Let's go. I'm going to go down and pick up your question sheet. You can start on 13A.
He's still alive.
Come on and pass it on.
I was doing I was revising the yeah, and I think it's the one with like inverse and stuff. And
7F.
Sorry, 7. It was finding like if AX is this, find X.
Yep.
Yeah, I couldn't do that.
All right, we'll do it together.
Yeah, when?
Right after I finish off this example, stop the video and we'll do it together.
Because no, I can do everything else, and I got to that, and I did it on the test, and it gave me different answers.
Oh.
So I thought maybe the textbook goes wrong, but
Could. Potentially.
otherwise, then I'm doing something wrong, even at work. So.
All right, I'm going to go through the answer. You can check your method. Your method could be different to mine, but as long as you get the same answer, right? So here we go. I don't like divisions. As soon as I see divisions, I try to get rid of it. That's just my own personal preference. I like times better. Okay? So I would expand the brackets here first. And instead of dividing, I'd change that. So this is technically the same thing as writing AB negative 1C cubed all over 1. So when you divide it, it becomes now 1 over AB negative 1C cubed times with, now I'm going to expand the brackets. This becomes 2 cubed A9 B6 A cubed B3 C6. So I like to expand the brackets out so I can have them in their individual terms. So that means I'm going to expand the denominator of the right hand side as well. So this now becomes 1 over A cubed B negative 3 C cubed. This is still 2 cubed. I'm going to write it out all again. So that's A9, B6. I'm going to keep the letters next to each other. B cubed, B3, C6. Now you see, from here, I like to just work with letters individually. So I would stick with the A's with the A's, B with the B's. Then over here, I'd do the same, but there's no A's or B's on the top. Okay, but there are B's and A's on the left-hand side, so I can cross-simplify. So from here, let's cross-simplify the left-hand side first. I'd say a to the power of 9. A to the power of 9. I've got 9 of these A's on the top here, and I've got 3 on the bottom. But remember, you've got another 3 on the bottom here as well. So that's 6 on the bottom in total. You've got 9 on the top. So naturally it makes sense if you got 9, take away 6, 3 on the top. Okay, so for me, these all will cancel out, and I should have a to the power of 9, take away 3, which is the same thing as saying a to the power of 3. Yeah, because 9 take away 3 is 6, 6 take away 3 is 3. Yeah? So that's the A's. I'm still keeping the 2. 2 to the power of 3 is still 2 cubed. Okay? Now I'll do with the B's now. So the B's, B6 divided by B3, but I also know that this is a negative 3. So what I really have here is times B to the power of 6, take away 3, take away negative 3. Because when you're dividing, you're take away. See, I wouldn't switch this B up. There's no point. There's no need. I'm just going to collect the B's together. This just means B to the power of 6 divided by B3. Or you can say it's B to the power of 6 divided by B negative 3. When you're dividing, you subtract. So it's really B6, take away 3, take away negative 3. Yeah? But these two will cancel out. Negative 3 plus 3 is 0. So I have now B6. These cancel out to be B6. That's all in the numerator so far, by the way. I'm just working with the B6s, so it just tells me how many B's I have. In the denominator, I've still got C6 times C3, and there's nothing in the numerator, so this will stay as C6 times C3, C9. You add the number of C's you have. 6 on the bottom on the left, 3 on the bottom on the right. 6 plus 3 is 9. Okay? So putting them all together now, that just tells me the answer has to be 2 cubed, which is 8, A cubed, B6 over C9. Hands up if you got that correct.
I just wrote this wrong.
Okay, so it doesn't matter which way you do it. There's a lot of different ways that you could have got it. This is just my approach for myself. I like to keep the letters together. I don't like dealing with the negatives. I just times and divide. I stick to 2 rules. Rule number 1, rule number 2. I like those rules because I don't go wrong from there. I don't make it more of a fraction. I don't use any crazy rules. I stick with 1 and 2.
I wrote 8 times 8 and 3 times 3 is 6. times c to the negative 9.
Say it again?
I think if you times it all by c to negative 9, is that the same as dividing by c to 9? No, because that way you're only multiplying b times c to negative 9 and not the whole. Yeah, a, b, and c.
What's that again, Seb?
I instead of putting c to the 9 on the bottom, I just times the numerator by c to the negative 9.
Oh, so wait, did you do so like
Can't be
like that?
Yeah, that. I can't see why that.
Yep, that's fine. Because essentially this is the same thing as writing 8 times a cube times b6 times 1 over c9. Because they're all timesing, and so therefore you can rewrite it as 8a cube b6, and switching the 9 up becomes c negative 9. But why wouldn't I suggest you to leave your answer like that? No, it's not that it looks stupid, but when you leave your answers, you never leave your answers with negative powers. It's just the format. So though it's correct, in the examiner's reports next year, they won't want you to leave it as negative powers. So you have to change it. Okay? All right. Thank you. Exercise 13A. Practice your index laws, because all of that is going to allow you for 13B to solve. We're just revising skills, and then 13B is solving. You can only solve if you can simplify. Just like you can only solve if you factorize. Factorize null factor. Same idea with this one. You can't solve if you can't simplify.
Because he still wanted to use the rings of power to save his people.
I'm going to stop the video. I'm going to help. And Anna, I will make a video today. I got a bit more time today. So yesterday was parent teachers.
We don't know that.
Okay. I'll make a video about CAS. You got your SAC tomorrow. Don't forget. Get your SAC. You can bring bound reference if you need, so you can bring in your textbook if you want. It really doesn't help, but you can if you want. CAS as well. Don't forget your CAS. Just one SAC.
Is there a